I'm Maarten van de Perre, and I'm Specialist Solution Architect in AI and Application Development at Red Hat. This video is an add-on on a blog post that we've created as part of our Road Towards AI blog post series. It covers a basic, high-level explanation of AI model designs. The link to this blog post will be added in the comment section afterwards. One type of AI models that we're covering during this blog post are neural networks, which are visualized in this video. For data scientists, if you are a data scientist, keep in mind that I'm bringing the message as high level as possible, so please don't fight over shortcuts I've taken in this video. So let's now start with the neural network itself, which looks a little bit like this. You can see it as an artificial brain, where you have neurons, the circles, and synapses, so the connections in between these neurons. Each neuron receives inputs, processes it, and passes the result to the next layer of the network. Neurons in one particular layer are connected to neurons in subsequent layers through weights. Be careful. In this image, for example, we have two input neurons. In the real world, this will be millions or billions of input parameters, input nodes. Talking about input nodes, you see that we have three color schemes over here. The first one, the orange layer, is the input layer. This is the first layer that receives raw data or features. For example, pixels of an image, text, sensor data, and so on. Then we have a greenish output layer. This layer provides the final result or prediction. For example, a class label, if the image contains a husky or a wolf, for example, a probability, continuous value, or whatever, can contain a lot. Again, I've drawn two over here, can be millions or billions in the real world as well. And then you have a couple of red layers over here. These are hidden layers. These layers lie in between the input and the output layers, and as you will see in a second, perform complex computations. And then you have the weights, which are not yet visualized over here, but are part of the connections. So each connection in between these neurons has an associated weight with it. This weight is adjusted during training. Weights, as you will see in a second, determine the strength of the inputs and influence the output of the neuron. Now, I was talking about weights, connections of these neurons, training processes. How does this look like on neuron level? For this, I found an interesting visualization on this blog post. So this shows now the diagram, a visualization of a single artificial neuron, which is the basic building block of neural networks. So what's shown in the diagram? On the left side, you have the input parameters. So the input nodes with values 1, 2, 1.2, 2.1. Then you have weights on the connections. So each connection between the neurons has an associated weight, which adjusts during training. These weights determine now the strength of the input and influence, as said before, the output of the neuron. Then you have a net input function. This shows a summation, calculating the weighted sum plus the bias resulting in a certain number. I'll come back to the bias in a second, but then as the last part towards the output, you have an activation function. For now, in this visualization is a sigmoid curve, as you can see over here. In a second, I'll show you another option there too. And an activation function, in a neural network, you can see it as a curve over here showing a transformation of the net input to produce the final output. An activation function in a neural network decides whether a neuron should be activated or not, based upon the information, the summation it receives. Think of it a little bit like a switch that you can turn on or off based on the input. It helps the network learning to learn more complex patterns rather than just basic relationships by introducing non-linearity. I've told you that sigmoid curves are one option. Another option are, for example, ReLU curves. ReLU is one of the most common activation functions and can help the network ignore irrelevant information, for example, negative values. So these are two options in the activation function. Then I skipped bias for a second. The bias is a constant input value that shifts the activation function. A bias term is added to the weighted sum of inputs to a neuron, helping the network fit data better by shifting the activation function. Bias acts like an intercept in a line equation, allowing the network to shift the decision boundary up or down and handle more complex data. In simple words, neural networks' biases can be defined as a constant which is added to the products of features and weights. It is used to offset the result, and it helps the models to shift the activation function toward a positive or negative side. So this is now a visualization of a simple mechanism that forms the foundation of neural networks, where millions or billions of such neurons work together to solve complex problems. The weights and the biases are the parameters that are adjusted during training to make the neuron respond correctly to different inputs. It are as well these values that are shared in the open source models that they're talking about. And it's a term that's often misused because it's not 9 out of 10, it's not really open source. It's just that the weights and the bias values are shared, so it are some kind of open models. But to make it open source, you need more than that, but more on this in other blog posts as well. Now, how does this look like when the neurons are playing together? For this, let's zoom out a little bit and let's see how a neural network behaves when we do handwriting recognition, for example. Again, a blog post with a visualization I really like. And here you can imagine you're looking at a snapshot of a neural network designed to recognize handwritten digits. On the left, here, you'll see a 28 by 28 pixel image of the digit 2. All 784 pixels from this image are fed into the first layer of the network, one neuron per pixel. Each neuron in this input layer then connects to every neuron in the subsequent hidden layers. And those hidden layers ultimately connect to an output layer of 10 neurons. This is then, these 10 neurons correspond to possible digits from 0 through 9. In other words, the network is basically asking itself, how likely is this image to be a 0, a 1, a 2, a 9? At each layer, the network assigns weights to the signals passing through, and it adds biases to control how these signals are combined. By passing the inputs through multiple layers, the network can learn increasingly complex features, starting from simple edges or curves in the first hidden layer and building up to more abstract concepts like the shape of certain digits in the deeper layers. Finally, in the output layer, the network uses an activation function. Network uses an activation function that produces a probability or probability-alike score for each digit. Whichever neuron in the output layer has the highest score effectively becomes the network's answer. When you see a glowing line or connection in the animations like this, it indicates the strength of the signal, which is then very bright. That weight, if it's very bright, is having a strong influence on the decision. If it's dim, the influence is weaker. By training on thousands, millions, billions of images now, the network fine-tunes these weights and biases so it can accurately recognize digits it never seen before. This is the essence of how machine learning can look at messy, real-world data, like handwritten scribbles, and then learn to classify them with a remarkable accuracy. So this is the high-level explanation of how a neural network behaves. Link to the blog post will be added in the comment section of this video as well. Stay tuned and let's see further blog posts.